few words about me. I'm Martin and I work at PEX. I talked with some of you already about what PEX is, what we do and so on. I maintain Catch 2. Some of you may know that as well, but I am not here for either of these two reasons. I'm here for something else, which is, well, perfect code, right? And it doesn't exist, right? But, well, I disagree because I found it. And I will show it to you and I will prove to you that it is indeed perfect and there is nothing we can improve. So, as one does, I was writing better Sin. I needed my own implementation of Sign and I wrote it and it was perfect. But why was it perfect? Well, let me show you something. These are tests. There's actually quite a few tests here. No, sorry, this is first benchmarks. Because of course, if you write your own math library, you need benchmarks. And I know that the performance of Sign is input dependent, so I went through different data types. I tested the, normal numbers that you will find. I've tested the huge numbers, which will need to be reduced down to something that you can actually use before the computation, and I tested subnormal numbers. And then I compared my Sign implementation with std Sign. By the way, this all is written in Catch, in the generator and benchmarking support in there. And of course, it was faster, right? If it wasn't, why would I be talking about it here? You can see some pretty graphs. And you can see that here for the common inputs, my implementation is, 4 times faster. For the huge inputs, it's 7 times faster, let's call it. And for subnormal inputs, it's just a little bit faster. Now, yes.
Is your performance like completely independent of input?
Yes. It stays good, right?
Well, do some cryptographic library that.
Yeah, I'm telling you, this is perfect. So, of course, I wrote tests, right? You need tests for these things. So I wrote first just a simple case, because what's sine of 0? I mean it's 0, right? And there is some margin because we can't expect the number that we get to be the one that we write. Or rather, we can expect it if we write it with enough precision, which 0 is, but then for more complex inputs, you find yourself writing these many, many hex digits of the double that you expect to get. But I did not stop here, right? One test. That's not enough. More tests. I took some numbers. I took pi. I took some numbers that I smashed the numpad for, and I checked some properties hold. One, I checked that, better sign is symmetric, just as sign is, right? The function is symmetric around 0. So we know that sine of x is equal to minus sine of minus x. And of course, I checked that I agree with std sign, and that std sign, gives me the correct result. And I ran the tests, and they all passed. Right? We see, this is good. This is great. Right? So, this is the perfect code. Are you ready for the implementation? This is it. You can see it's very fast. It's constant time, and of course, it's it's completely wrong, right? Anyone here doesn't see why this is completely wrong? No? Thank you. We can proceed. So let's talk about it again. Who really doesn't agree that this code is perfect? Come on, hands up. Everyone disagrees that this is perfect, right? Hi. Well, no, but okay, this is your opinion, right? The code is perfect, and I can prove it to you. I will do this. I will prove it to you during this talk. Because, that you say it's not perfect, that's your subjective opinion. Let's look for our tools and ask them for some more objective answers to our questions. So, what is the first? So let's talk about tooling, what we will use. What's the first tool in our feedback loop? When you write C++, what's the first thing that tells you, no, this is wrong? Clang compiler. Yes, exactly. So let's talk about compiler warnings first. Now, compile warnings are very useful. They will quickly diagnose some issues in your code, like this one. Who here sees the problem already? Okay, I see some people with their hands up, right? Who here would see the problem this quickly if I didn't just tell you this there is a problem? Like much fewer of us. So let's ask a compiler, right? Let's ask Clang, and it will tell you, yeah, you initialize these data fields in the wrong order, and this will do bad stuff at runtime because you don't know what this will actually be, this value. Cool. The warnings and the compilers are our friends, and they are the very first thing that will tell us, hey, this is wrong. And the thing about warnings is that they need to be fast to check, and they have to have very low false positive rate. Right? It's fine for them to have pretty high false negative. That's what we have other tools for. They just have to have very low false positive rate. For example, since I said they have to be fast, it takes, I think, 10% of compilation time to there is 10% in compilation time difference between compiling catch to the test suite with warnings and without. That's fine. 10%, we can afford that. Anyway, so let's ask the compilers about better sign. So first, let's ask Clang. And one thing I want to point out is that Clang does have this flag warning everything, which does exactly what it says. It gives all the warnings. Oh, and it is completely fine with better sign. It sees no issues, right? So it thinks it's perfect. GCC does not have warn everything flag. So we enable some groups of warnings, like take a guess at what we want, and it's fine. Plot twist, MSVC does have warn everything flag. It's called all, because of course it is. You literally ask for all the warnings. It's just GCC and Clang that are weird. And yeah, it also says, yes, this is good code, great code, no issues here. So the three major compilers all agree with me that there are no flaws in the code, right? Who here in this room disagrees with them? Yes, some people, of course. The rest of you are already asleep. No. So let's talk about static analysis, right? And the thing about static analysis is it's much more expensive than warnings. And I do mean much more expensive to run than warnings. Again, like very rough ballpark, we are using Clang Tidy in our CI. And while our CI build uses 8-core machine to compile our code base in about 3 minutes, the Clang Tidy job uses 32-core machine to spend 10 minutes. There is significant difference there. But static analysis is still very cheap. It can easily be like the second thing in your feedback loop. If you are using, I think, JetBrains CLion, it will actually run static analysis in the background on the file that you are working on. MSVC has its own like analyze mode that you can enable and this sort of stuff. And I want to show you this as an example of what your static analysis will find, but your compiler won't, right? This code is a bit overcomplicated because it's hard to get like realistic example on slide. But if you look at it for a while, you will see that it actually will cause an issue here, right? If not A, then you can write here, and that's a problem because we are just writing into free pointer. Let's ask Clang Tidy. Clang Tidy is awesome because it's free, it's open source, it's based on Clang, so it understands C++ quite well. You should use it. And it will tell you, yep, there is a problem. You are using this memory after you have released it. Well, let's ask Clang Tidy about better sign. So who here has used Clang Tidy before? Yeah, quite a few people, nice. But let's go quickly over how you set it up. So first, you have to configure your checks. You say, okay, let's check for everything. Don't do this on your production code base. It will take forever, and it will give you infinity warnings. But we will do it for this proof, let's call it. Then you have to set up your project. This is standard CMake project setup. These are the important parts. First, hey, use clang tidy as clang tidy. I know this is like really riveting stuff. And then we can run the build as you would normally do, and it will actually put out all the clang tidy warnings as if it was a part of the compiler output. Now you can see already quite a lot of output. So did clang tidy find an issue with better sign? No. Let's look at them, right? First, the declaration must be enclosed within libc namespace declaration. Why? Because if you just tell clang tidy enable everything, it will enable everything, and it has warning family for, hey, I am writing LLVM libc. So, this doesn't help us. Then it will tell you, hey, there is no header guard. No, there is pragma once. Quick check. Who here likes header guards more than pragma once? Okay, I see two people. Who here likes pragma once more than header guards? That's 5 people. Yes, you are correct. So technically, okay, man, it's quite not standard, and technically, in some cases, you might find that the compiler thinks it's a different file, but it's the same file because you have it mounted once through this network file, and then you have it mounted twice through this network file, and somehow you put both of them into your include path, and then you will listen to the Bloomberg engineer who always complains about this, talk about what happens, and then you are like, okay, but why do you have the same file mounted in 5 different places and all of them in the search path? I don't know. There is one single place.
People say this and put them all together.
Yeah, I don't know. There is one company that I know that complains about header guards a lot. It's always Bloomberg. I don't know you.
Actually, there is one more advantage to compile guards. What can happen is that sometimes you want to put somewhere a macro that checks if something wasn't booted or not. If you want it to be like,
yes, that is true.
If you want it to be like an optional dependency, you can check, okay, if it is included, we are going to compile also discrete hashes, otherwise.
Yes, it's true. If you want to detect what else was included in the file before you, then you can use header guards to do that. And then you can auto configure your library to what it compiles. This is true. Don't do that. Don't. Because then someone will go into the file and be like, you know what? I think our include files should be alphabetized. What? And it's broken. Goodbye.
Maybe there is one thing, and that's the exploring dependency. If you need an extra dependency, you don't want to have an extra dependency for something that probably will not be needed because
check in your build system. Use your build system to do its work and check that you have the dependencies and what configuration you should build them in.
the more if you just remove a dependency this way, make something optional, just avoid all the problem with having too many dependencies. You just reduce the overall from one dependency has 2 dependencies of its own to one dependency has 1.5 dependencies of.
Yes, do this in your build system. That's what it is for.
It's a bit fun. CMake flags.
Yes, just find package. If you are using CMake, if you are using Bazel, there is something there. Anyway, let's move on. I did not want to get into the weeds about header guards, but so the first thing after you set up your clang tidy checks is that you have to go and start going, okay, I don't want these warnings. LLVM libc. There is actually many families of warnings that are hyper-specific. I am not quite sure why there are so many. Why are they all in the upstream of clang tidy? But you will find yourself disabling, I'm going to say 8 to 10 families of warnings because they just don't apply to you. Anyway, let's rebuild and see where we are at. So we still have some complaints, and it's about trailing return time for this function. Don't say double better sign, say auto better sign, and then trailing return type. Quick question, but we will not go into another discussion. Who here likes the trailing return type for simple functions more? Quite a few people. The back row, interesting. I don't, but like this is a subject of taste. Fundamentally, I don't actually care. And there is still the pragma ones, so we will tell ClankTidy to shut up about these two as well. And now we will finally ask, hey, so what do you think about the implementation of better sign? And it will say, hey, oh, this is completely fine. If you don't care about LVM libc namespace and you don't care about pragma ones, it's perfect. Well, notice one more thing. I'm cheating it a bit. I ask him, hey, the implementation, not the tests. For the tests, just to show you that I don't have much up in my sleeve, you have to disable a few more warnings. One of them is Altera. This is family of warnings for some SDK for some specific device. I don't remember. And then I actually hate the last check a lot in ClankTidy. If you have something like for int I in some numbers, and then you just do simple operation, it will say, but hey, like the identifier I is too short. And you can disable this. You can only disable this for index loops, but not for each loops. I don't know why. Look, like, no. Anyway, yeah, so ClankTidy agrees. Better science, perfect. There are no issues there. Let me refresh your memory. This is the implementation. So who here still disagrees with ClankTidy and your compilers that this is perfect? Yes.
Do I disagree with
You disagree that it's perfect. So who disagrees is perfect? Yes. That's more people than before. But like, that's your opinion. Let's ask more of our tools. So static analysis sees nothing wrong, right? And we have tests. Those tests passed. We had benchmarks. Benchmarks that said, yeah, this is great. What do we do if our warnings, our tests, and our static analysis don't find an issue? What's the next? Well, we have to look into the test deeper, and specifically, we will look into dynamic analysis, right? And where static analysis just looks at the code in situ. It doesn't like see what it actually gets for inputs and so on. Dynamic analysis runs, sometimes instrumented, sometimes not, binaries, and looks for errors inside these runs. And it has a big advantage, right? You can find issues that are state dependent, and it has roughly 0 false positives, right? Your static analysis will never warn you about, hey, this addition of 2 integers might overflow, because it would have to warn everywhere. Your dynamic analysis will tell you these 2 integers, when you edit them, overflew. These were the inputs, fix it. And you know that actually this problem is there in your code and it happened. Right? So
there is overflow and I don't care or something?
Then you still have a problem, because if the compiler sees it and listens through it, it can delete your overflow check and do whatever.
Well, no, I mean a different situation. I just add a bunch of numbers every time I go there. I don't care about some of them. And sometimes they overflow, but for some reasons I know that these I don't care about to overflow.
Oh, if you like know that you have a place in your code where the integers overflow, then 1, they shouldn't be signed, they should be unsigned. 2, you can say, I don't care about unsigned overflow, and you can usually both specify either in general or here. Anyway, let's take an example from, actually, I found this at my work. This is slightly changed to protect the innocence, but I found this function, and it has an issue. It exactly overflows an integer. I will show you, like, we don't need more than this to see the issue. Just ask this for random seed for your very first thread ID. And when you ask Clank, just tell me everything about this function, it will say nothing. Same for ClankTidy. But if you actually ask you use the dynamic analysis through sanitizers, specifically undefined sanitizer, it will tell you, hey, yeah, you overflew your signed integer. Don't do that. You should not be overflowing signed integers. overflow unsigned integers. So anyway, let's test better sign with our sanitizers. Let's go back to our CMake project. And the only thing we have to add to get sanitizers is this. Well, technically we have to say, yes, we want to use Clang. If your environment is already set up to always use Clang, then you don't have to do that. But for CMake, you say, okay, flags, sanitize, address, and undefined. This is like the basic set that you should always be running your tests with. There are more sanitizers. You may have heard about memory sanitizer, which is really annoying to use, and thread sanitizer, which is slow. Not as slow as Helgrind with thread checks, but it's slow. And we run the tests, and we find out that there are exactly 0 issues that sanitizers will tell us about. So, we tested other sanitizer and UV sanitizers, and it found no issues. So, I again posit, this code is perfect. You can't prove that it's not. We asked a lot of the tools that we use, and it still says, yeah, this is perfect. There are no issues. Well, yeah, so who still disagrees that it's perfect? Yes, few people still disagree. Great, but again, well, that's your opinion. So we ask our compiler, we ask static analysis, we have tests, we try sanitizers. By the way, yes, if you run it under Volgrind, it will not complain either, right? So we need new idea. We are debugging our issue and we need new idea. What if the tests aren't sufficient? And thus, how can we tell whether the tests are or are not sufficient? So we will use a very common tool in this space, which is code coverage, of course. Now, the thing about code coverage tells you how much of your code you exercise with your tests. Or if you want, it tells you how much of your code is untested. And of course, quick note, it tells you how much of your tests were run, not necessarily whether you actually checked them, right? Anyway, there are many kinds of coverage, and I will talk about some of them, mostly very briefly. So let's go through them. First, function coverage. This is how many of your functions you even run. If this isn't close to 100, like 99 point something, because you can't instrument some special function, what are you even doing? Line coverage. Line coverage tells you the percentage of lines in your code base that were actually executed by tests, right? Each line counts once, no matter how many times you actually run that one line. For an example, let's take this simple function. It's quite frankly, again, it's slideware, right? It doesn't do anything interesting, but you can see that we have two bools and an integer, and if those bools are true, we just multiply the result a bit. Easy enough. Let's add a simple test. This is like the most basic test you can write. We just execute it through assert. So you verify both that you get the result that you wanted, and then you get the coverage. So what's the test coverage on this one test? Line coverage at this point.
And I was a big person. Oh, 2 lines and 1 column.
No.
Sure, that is executed, so your only 2 lines are key.
This is a problem, right? We already found the first issue. It's actually quite tool dependent. What is and isn't counted as executed. I'm going to tell you what Clang thinks. Clang says 6 out of 10 lines are covered. The ones in black are covered. The ones in gray are not. Why does it, split this? I don't know. Just look, it doesn't, in real code base, it doesn't matter, right? In real code base, you have thousands, tens of thousands, hundreds of thousands of lines. So little bit of difference in this, whatever. But yeah, Clang does think this is 60%.
But this is code dependent. If I just put the very and the inside clause of the same line with the braces, I would get 100% line coverage.
If your instrumentation tool is at least decent, no. But yes, it's a good question. What will your tool do? For example, on Windows, because I don't run with playing on Windows for reasons, I use tool that actually does behave like this, and it's kind of stupid. Anyway, for line coverage, we could get 100% with just single test, right? Because we say yes, enter both of the branches, we will get a result of 12, and this is indeed 10 out of 10 lines coverage. So we have 100% line coverage. Yeah, and we with one test got 100%. Line coverage is very basic, very simple to measure, and it doesn't really tell you much. So what's the next one if you want to be more serious about the coverage? Sorry, you? I will get there, but from but coverage. And you said?
Single branch.
Yes, branch coverage. So let's talk about branch coverage, right? It tells you the percentage of your branching options taken. Like if you have if else or just if, but you can skip over it, then it always gives you like 2 branch options. Then you can actually get into weed quite a lot. What does switch do? How many branches does switch introduce? I don't know. Depends on your tooling, but the basic idea is that technically switch should give you 1 branch per each label. And also, if you don't have default, then it should give you like 1 branch which just skips everything. Anyway, let's go back to our example, and let's have 2 tests this time. First, the one that gives us 100% line coverage, and then one more which gives us 100% branch coverage in total, when you combine these two, of course. Now, we did 2 tests. Once we entered both of those conditions, once we did not enter both of these conditions, and that gave us 100% branch coverage. Of course, if we made some different choices here, we could end up with very different coverages. Also, we could get to 100% branch coverage with cross, false, false, true, true as well. So what's above branch coverage if we want to be more serious about this? There are like 2 options. One of them is very well known if you work in safety critical software. The other one is the one that other developers actually know. So what's combination of branches? It's a path. And again, this is simple percentage of paths executed. And the path is enumeration of all the branches you took through your code inside the tests. Now, if we go back to this example, we see that we actually need all 4 possible inputs to reach 100%. Where is my pointer? We need all possible inputs to reach 100% path coverage. It doesn't matter in which order we do them. And also, this gets kind of annoying because, to get perfect path coverage, and if you have multiple inputs, it gets very, very big. The number of tests that you need gets untractable very quickly.
So it's also possible that some combinations scale in the log tree.
Yes, that's possible. Is it possible?
If you have
It shouldn't be. That's fine. Like if you have both of these times 2, that's fine. And
if you have the first checks for times 2, the second one checks for times 2, then you cannot get 100% back coverage because these 2.
You can. There is no path that's dependent on times 3. You just make it simple for you.
Like if this is not a trivial case, it cannot always be used that sometimes you are checking for the result of some operation that will cause one condition to be the same as some other condition.
No, the problem is slightly different actually, but fundamentally yes. If you use defensive asserts, post-condition checks, these are an issue, right? Because if I put in here assert, I'm not sure what's reasonable assert for this function, but if I put in here some assert that checks that like the logic in the function is correct, then I will never be able to trigger the assert fail if my function is correct. That doesn't help you either. That doesn't change anything.
Take an exception as a check in the best if an exception was thrown.
No, you misunderstand the problem, right?
If I got something that should have those.
Yes. If your postcondition assert or check or contract in newer C++ versions should never fire. It's always like, yes, I wrote this correctly and I just checked. And if it ever fires, you have much bigger problem than your coverage. Then you have check on the preconditions. Anyway, I now want to take a quick side path to different coverage types. Condition coverage. It's very similar to branch coverage, but not quite true. It says, okay, what's the percentage of Boolean sub-expressions that's evaluated true, false, right? This is actually what GCC and Clang will give you if you ask them for branch coverage. Why? Compilers, dudes. But they don't actually implement branch coverage, they do condition coverage. So that's why you should know about it. To explain, here we have two bools and we have an OR, right? So if either of them is true, we enter this branch. And the difference between branch condition and branch coverage and condition coverage is basically this, right? This should give us 100%, these two together should give us 100% branch coverage, and individually, both of them should give us 50% branch coverage. This last one gives us only 25% condition coverage because you enter here and you never ask for bump 2, what is its value, so you don't have coverage from there. And now let's talk about the big one. Who here does safety critical stuff? Nobody. You kind of, somewhat. So do you know MCDC? So MCDC is quite fun, and you will never run into it unless you do safety critical software, in which case you have to have 100%. That's just mandatory. There is literally law that you have to do 100%. And what does it mean? So for every decision, you have to check that every possible outcome was achieved. This is basically branch coverage. For every condition, you do every possible outcome. This gets us into the condition coverage. And then gets more fun. You can show that each check you did has affected the decision outcome independently. This actually complex to explain. Let's move on. But if you work in like aviation, automotive space, nuclear powers, all this stuff, then it's mandatory. Big thing, these two are not subsets, right? Your path coverage and your MCDC are not subsets of each other. Anyway, let's get back to our motivating example of this talk. What's the coverage of better sign? This is our function. This is our simplest test. This is the first one we wrote just for the sanity check. What's the coverage here? Right? What's the line coverage? Yes, bench coverage. Path coverage. MCDC coverage is 100%, right? We don't have to go through them. And just quick check. Is here anyone who doesn't see why it's 100% in all cases, the coverage? No, right? It's very easy. There are no decisions to be made. Okay, let's go back. All of our tests pass, and we have perfect coverage. 100% path coverage, MCDC coverage. Like, people can envy how good our test suite is. So the code is perfect, right? No? Come on, guys. Come on. Next question. We have great test coverage, but do the tests actually verify the implementation? Do they exercise it? Could they find the bugs in our implementation? Well, let's check. What tool do we use to do this? You already heard it here before. Yes, mutation testing. Who here has heard about mutation testing before? About half. Nice. Much better than when I was in München. So the mutation testing, it tests the test suite, your tests, not your implementation. It basically looks for, hey, are these tests able to detect changes in your implementation, right? And it does so by just introducing bugs into the implementation. It looks and it sees, oh, this line does A plus B. Well, now it does A minus B. Will the tests fail if you run this? These bugs are called mutants. That's why it's mutation testing. And yes, it uses like killed mutants and so on wording for the actual checks. Well, yeah, let's go over mutation testing a bit. Now, let's first look about, when you want to create mutants, in theory, there is lots of stuff, right? I already mentioned one. You turn pluses into minuses. You can just do this. You can do this without generally changing whether a code compiles. This is not always true, but it's true in most of the cases. And if the change causes compiler error, you say yes, mutant found. Some other ideas. Wouldn't it be fun to change in your code and then see what breaks? This is a good one. Another one. Oh, what if I say, oh, this is AND? No, sorry, it's OR. Just one of these conditions is fine. It will work. Also next question, and another thing, actually, what if I don't call a void function? What does the void function give me? Nothing. So just don't call them.
It's just a loading function.
This is a real problem. I will talk about it a bit later, but this is actually a real problem, like loading functions and similar stuff where the output is not checked for correctness. But yeah, you can just call function, you can replace, calls to functions with some constants. You can do lots of stuff. And I do mean lots and lots of stuff. For example, with this trivial code we have seen it once before, 3 simple mutants are, okay, what if we don't say OR, but we say AND? What if we say not add 1, but subtract 1? And of course, what if we add different constant than 1? And we have some tests. This is our test suite. And we will say, okay, now we will check all these mutants, run the tests, and count how many of these mutants we found. How many of them we will find. All of them? No. Yes, we won't find the first one. We will find 2 out of 3. We will find the changes in subtraction and addition, but our test suite just doesn't catch the first change. It would if we changed these around a bit. Anyway, this would be scored with 66% mutation score. This is somewhere between good and bad, depending on how well you have already pruned some issues with the mutations. Now, this gets into the part where I should suggest a tool to do mutation testing in C++. This is a bit of a problem. I did quite a bit of research. There are many mutation testing tools. Some of them are like, oh, this was research we made on top of Clang 6. It's like, Clang 6? Guys, that's not quite older than my code base, but by a little bit. I don't want to use mutation testing based on compiler that's is older than my code. So after some looking, I found Mul. It's the one tool I found that's actively maintained and free at the same time. This is quite nice when it's free. And how do we use it? Again, if you have your CMake build, then you say use this Clang version. It doesn't need to be 19. Well, it needs to be newer one with newer releases, but it has to match your version of Mul. And you build it slightly differently. You say, okay, look, this is actually a compiler plugin that you will use. This is how it can inject mutant into your files. And then you say, actually record the command line. This is nice to get output, but it isn't needed. Anyway, then you say, okay, build my tests. And then you can then you have to set up your mutators, which we will try. We will try all of them, of course. And then we will say, actually, we don't care for mutations in tests. We want mutations in the actual source code, in the implementation. And then when you run it, it will work for a bit, and it will tell you, actually, I didn't even find the possibility to make a mutant. Yeah, this can happen, like it has issue where it can't actually change constants for reasons which are tied into how Clang does some AST stuff. So, it can't change the one constant in our code, so it can't create any mutants, and we can go home because it has found no issues in our tests. So again,
to could probably make a small correction into the recurring constant.
yes, if it would make small, that's actually one of the tricky parts of changing the constants in the mutation testing. If you say this was a 0, now it's 0.00000001, then that's useless mutation test. Like, this will not be found, right? So you have to make a big change. You will say this is a 0. Now it's 42 for the constant change, and the test would find this because the tests check itself against std sign, and std sign can give you 42.
Is your mutation that's completely valid and will be verified?
I would say that it's not perfectly valid. This is actually a part that I quickly skipped over. When you do mutation testing, there is this big question of how do you deal with idempotent mutations, right? What if I have some template code that does some substitution and stuff, and then it says, okay, what we will do is we will take A and divide it by 1, because it was some type-dependent constants, and it just all simplifies into 1. And the mutation tool goes and says, let's not divide by 1, let's multiply by 1. This is idempotent because dividing by 1 and multiplying by 1 is the same. General detection of these issues is really hard. I'm not sure it's actually possible for all possible programs. And then there is lots of heuristics that will try to catch these idempotent mutations because they are, of course, useless. Anyway, yes, so better sign is perfect. And who still disagrees? Everyone. Yes, thank you. But again, it's your opinion. Let's ask another tool. So we did mutation testing, coverage, dynamic analysis, static analysis, tests, warnings. What can you ask in the year 2026 now for another opinion? Yes, you can ask LLM. LLM reviews are the hot new thing. If you go to GitHub, it will tell you, do you want to review this with Copilot? Are you really sure you don't want to review this with Copilot? But have you considered pinging Copilot to make changes into your branch and pay us money? And now, what I like about LLM reviews is that it, unlike all the other tools I have shown you today, it actually does kind of mimic human-like review. It will write you 10 pages of bullshit you don't care for, but in some ways, it's human-like. I will show you what I mean quite soon. Right? It does actually somewhat consider, or it does something that's adjacent to considering, if we want to be correct, names, your docs in the pull request, and so on. So let's ask Gemini. Why Gemini? Because that's what I had open on my notebook at the time. So what does it say? Here is a review. There is a critical flaw, and my pointer keeps being gone. It passes with the dummy implementation, return 0, and then it exactly tells you the trick of the generated numbers. This is basically all multiply of pi, and it's always 0. Yes, this is correct. It did catch it. First try, easily. Did it, though? So, what do you do when you try something like this? You try again, and you do experiments, and a lot of them. It's not supposed to be duplicated image. I need to fix this. Now, my Now the history for my work account Gemini is now forever, yeah, like this. So I want to show you some fun outputs that I got after testing some slightly different formulations, slightly different context, and so on. One is, oh, this is completely great, amazing, whatever. Everything's great, right? Oh, this still continues, just saying it's amazing, great, and so on. Yes. Now, so this was one interesting part. After a few tests and with slightly different wording, you can get it to just say, yes, it's great, merge it, ship it. Now, another attempt. This is pretty solid file, blah, blah, blah. Notice that it doesn't talk about the implementation anymore. What I did this time was that instead of giving it the context of the implementation, I just gave it the tests. And it did find a bug in the data generation for the benchmarks. Because I made a small mistake, so the subnormals numbers were slightly wrong. By the way, it's nice that you found it, like, good job, but it says absolutely nothing. Sorry, let's go back here. It says absolutely nothing about the actual problem with the implementation or that the tests are all fake. It just goes, no, there is a small bug in how you generate the data for your benchmarks. Another attempt. This is actually very close to finding the issue. This is after I fixed the data generation bug and gave it again. Blah, blah, blah. Yes, good. It's very loose, the tolerance that you have, and it is correct. But I could fix this easily, I would just have to be less lazy about writing in the approximations of pi multiples. But it did find, hey, there is something weird. So, does Gemini agree with me? Is the code perfect? Depends on how you ask it. When do you ask it? Do you give it all tests? Do you give it the implementation as well? So maybe I'm going to say yes because I eventually got it to agree, and I can just show the one review that I care for. Let's recap. So the perfect code exists, right? It's this. We verified it with static analysis, tests. We verified the test with coverage, and mutation testing. We did dynamic analysis. We asked Gemini, and they all agree. This is perfect code. Thank you. We are done here. Okay, no, I just needed to drink a little bit.
I was actually lazy for this is for Joe.
No, so recap, not for real this time, actually. Like when you write code, there are many tools that you can and you should use to write correct code. And the thing about them is that they all protect you from Murphy, not Machiavelli. They all protect you from you having a brain fart and writing something wrong a little bit. They don't protect you from some asshole like me just going, yes, I have engineered my test and implementation to be wrong.
But actually, it's not like you don't have to engineer this. If you're writing in calculator and the product of corner case, that code is sub the result to be very wrong. There's absolutely no tool that will fix it. Because if you don't sketch for that specific corner case,
Yes,
pass exactly the way you are describing better.
yes, but counterpoint, if you know that these like corner cases are there and you test for them, then your test will already catch it. Yes, yes, your bugs and your forgetfulness for writing tests can also help each other to get a bug through. Anyway, you have to understand the limitation of that tooling, and what does it tell you when they say, yes, this is perfect, this is great, this will work. So let's go over the tools once more very quickly. So first, static analysis. This includes warnings for this. So first, you do not need tests. This is actually very useful, right? Because sometimes you are writing more code somewhere in the middle of, like, deep in your code base, and your compiler and your static analysis will already tell you, no, I don't like this is probably wrong, even before, not only you can write tests, before you even have the API to write tests against. Now, the code does not even have to be runnable. It doesn't have to be compilable. Like the tools usually have some mode where they will approximate the checks and tell you, yes, up until now it's good or not. This means that it can run in the most inner part of a development loop. Your IDE can already tell you, you have this compiler warning, this won't compile, this is weird, no, don't do this. What are the issues? Well, first, the compiler, the static analysis tool has no idea about your requirements, right? It's blind to runtime behavior. The requirements, right? It looks at the function, better sign. Does it know what sign is? No, but it sees that the function looks correct. It does something. It is blind to runtime behavior. And it's also optimized for low false positives, for low number of false positive and scalability. Right? I want to go over this again, but when your compiler tells you, hey, this is an issue, it can't tell you, like, this place could overflow your integer, because that would just trigger a false positive on every single line in your code. Remember this example. The compiler can't tell you about this, because then it would have to tell you about every single issue everywhere, ever. Dynamic analysis. So what were the good parts of dynamic analysis? First, it can and does catch state-dependent issues. If you if you need specific arguments to your function to see a bug, yeah, that's not a problem. It produces basically 0 false positives. Notice basically 0. For example, we have suppressed 3 tests under Valgrind, like don't report the issues under Valgrind. And one of them just straight up crashes Valgrind. Second one, Valgrind says, actually, there is small issue, which is that I ran out of some internal mempools. And the third one takes, I don't know, like 8 hours under Valgrind. So too much. What are the cons? Well, the code has to run. And of course, your dynamic analysis is only as good as your test coverage. If you didn't write tests that would expose some issue, then your dynamic analysis will never tell you, hey, there is a problem here. It will just fail. It will fail to find it. Now, cloud coverage. The good, well, it does show you relations between your tests and the actual code. Note that I'm very careful to say relations and not correctness or something else. It will tell you, hey, you have tests and you don't test like this function or this branch at all. Maybe fix it. And missing coverage, actually, even if it doesn't tell you, hey, this is correct or wrong, it tells you, when refactoring this part of code, careful. Because if you change some behavior, you have no tests that will tell you you changed the behavior. And you don't know what relies on it. Like what customer will come in and say, guys, you broke me, and now I need it fixed. The problem with coverage, well, it's easy to game. We saw like how small changes in your tests can completely change your coverage. You don't have to check output of your tests. You can just execute your function with some arguments and then be like, yes, this is correct. I have the coverage. And your coverage is independent of whether your test will actually catch any bugs. It's also independent of your test correctness. You can say, I handpicked few inputs that are good, and then, yeah, that's it. I want to point out a quote by a very smart person made many decades ago. When a measure becomes a target, it ceases to be a good measure. Right? This is called Goodhart's law. And basically, if you take coverage, you should not have it be a metric on like, we must have 90% line coverage. Because the first thing that your developers will do, okay, I will make sure there is 90% line coverage. I can always do that easily. Similarly, you can game every coverage type, including MCDC. MCDC coverage looks very complex to game until you realize that it doesn't count lookups into arrays as branches. So you can just like have most of your function untested by saying, actually, this is not like 5 ifs, this is a lookup branch. Of course, quick note, I did say that for LCDC coverage, you are required to have 100%. So, if you work in, say, technical stuff, then you will have 100% LCC coverage. It's kind of stupid, but well, here we are.
There was one more specialty with this test coverage. In two studies were contemplating a rule that what if we increase the what if we make a requirement that every commit must not change or increase the code coverage? Then it turned out that the code coverage runs are stochastic and having help is plus and minus 0.1%.
Yeah, I actually have something similar for Catch 2. It will flag commits that where the coverage is too low, or it's significantly, not like by 0.1% or something, but significantly changes coverage. This is actually a useful signal, right? If you make a commit and your coverage goes from 80% to 50%, then either you just added a few 100,000 like untested code, which will be caught in review easily, or you somehow just disabled a lot of your tests from running. And this is actually kind of a big deal.
Usually one of these are intention. Because if you disable a lot of tests, this usually done where you are making sub-edge changes. And you need to disable those tests.
In my experience, no, but I can see why it will differ. My experience is that most often this is something like if you know Go, Go does testing by saying, okay, so all functions that start with test.
It's okay.
No, I mean Golang. So it goes, okay, so this function starts with T, EST, and then another uppercase letter. Yes, this is a test. I will run it as a test. But if you do something like write T, EST, and then lowercase letter, because you had a brain fart or whatever, well, it's no longer a test and it will no longer run. There is a lot of similar issues you can run into. So yeah, my experience is that more often you broke something that you didn't even know can break, because usually it's all just big Jenga tower of dependencies that kind of hope that text parsing is enough to identify your tests and run them. Sorry, let's move on. Mutation testing. The great thing about mutation testing is that it will actually tell you, will your tests catch bugs? It will tell you, hey, your tests or code doesn't handle this edge case at all. It can identify useless tests. If you know that some test does never ever catch a mutant, why do you have it? If there is no way to change your code to have this test say this is wrong, then why does it exist at all?
Because we want to be careful about something we didn't add yet.
It's possible.
I also want to add the checks for things that, well, can break. Sucky people make some change, but currently cannot be looked by. It can hold a implementation for the future.
Yes, yes, but at the same time, you would expect that if I just start breaking the implementation, then the test at some point will say no. If I change the internals of your function and the test still doesn't say no, it's suspect. Of course, you can add tests for the future, in which case, or rather in general, if you decide to use your mutation testing to identify which tests you care for and you don't go commit by commit. You go trend lines over time to see if it ever became a useful test or not. Now, what are the cons? Well, actual real product code, not some library, will have infinity of mutants that you never ever will care about. Like, oh no, my logging macro has changed the string that's inside it from I caught 24 fish to 24 fishes. Oh no, what will I do? I don't care. Another problem, they are very, very slow to run, right? Because in reasonable code, you will find millions upon millions of mutants. And even with pretty optimized implementation and parallelism and so on, running millions of your test test suites against your binaries against your test suites, that's a lot of tests to run eventually. And of course, it's limited to white box testing, right? To do mutation testing, you need to have some access to the source code, because doing mutations on the actual binary is really hard to find useful mutants that actually can do something. And even if you find them, then you can't map them to the source code and say, this is good, this is bad, does this make any sense? And of course, implementing mutation testing is hard. So there are very few available tools that you can use. And finally, LLMs. They're good. It's actually broadly applicable. You can give your LLM wide variety of languages. You can give it your code in wide variety of progress, like finished, unfinished, ask about stuff. It has kind of context between like your docs, your test codes, your strings. Example that I had recently, which by now means actually 9 months ago. This was the documentation. The argument P or path filter must start with either C for section filter or with G for generator filter. Simple enough. This was the test. Generic password without semicolon is rejected. These tests are correct, right? The test is test that this is rejected correctly. But there is a small little problem. It's not a bug, it's just code smell. Right? It's here. This is colon. This is semicolon. Because when I was writing this, I had a brain fart and went, actually semicolon, definitely semicolon, yes. And LLM, I did use Copilot for this, and it will tell you, yes, this is wrong. Maybe, maybe not. Depends on how it feels that day. Which brings me to the biggest problem. It's non-deterministic. Asking slightly differently, with slightly different context, at a different time of day will give you different answer. This can be a problem.
Actually, everyone's are deterministic, but the problem is that
you give it a random seed. Yes, they are non-deterministic for all purposes.
Yeah. And make it deterministic. Maybe you said that we change one symbol at one place and the rest will become unpredictable.
Yes. Okay, so technical comment. Technically, they are deterministic, except that, you seed them, so they are non-deterministic, but you could determinize them. Anyway, an issue that I have with LLM tools is that their false positives and sometimes false negatives are really annoying. This is kind of a me problem, but at the same time, if I have clank tidy check and it tells me there is a possibility of use after move in this test file, and I look at it and go, oh, I see the problem. The problem is that the check for use after move is flow sensitive, but not path sensitive. So this is a false positive. And I will have to disable this check. It's like, okay, fine, I understand what's the problem. When LLM tells me there is a bug in line X file in file C, and I look into the file and the line doesn't exist there, it's like, no, what the fuck is this shit? So my personal opinion is that the false positive from LLMs annoy me way more than from other tools. Sorry. There are some security privacy concerns. If you don't use self-hosted, if you self-hosted, then it's slightly better. For example, me personally, for the main project that I work on at work, we are not allowed to use non-self-hosted LLMs at all. We don't want to send this code to like somewhere else. And due to the combination of the really annoying false negatives and non-determinism, it builds false confidence. Because today I asked Copilot, review this pull request, and it says, yes, I found this and this bug. You go, yes, I fixed it. Then you ask tomorrow, and you will have the same bugs, but it might not find them this 2 days. So you will be like, yes, there are no bugs. No, they are there. Your LLM just didn't find it today. Yeah. So in conclusion, we have tools to help us. Use them, please. Thank you. The end. Now it's time for questions.
Highlight what is like the best run strategy for finding something meaningful.
No, not really. You have a question?
Have you tried the automated reasoning tool?
Sorry, automated reasoning group.
Automated reason.
What do you mean?
Basically let the program to like you describe some, let's say, environment in which this function of yours operate, and then it will try multiple times to go through it and reason about it. It's a framework. It's not that
Sorry, can you say the name of the tool again? CN. Okay, I don't know that one. I used TLA Plus at some point. It's very nice. It's very helpful for large integration stuff, basically, because it's really hard to go from this is generic C code, and this is the description of this is automated description of the C code. It's quite easy to say this is a function, it does this, this, and this, and then describe the whole system in some automated proof assistant and see if it finds some issues or not. Personally, I used TLA Plus and Alloy, I think it was, and UPPALL or something. One of them is for automated reasoning, the other one is for timed automata. They can be helpful. I have found it hard to get places to invest in using them. It has to be like very important stuff. Like I know that, for example, when NVIDIA was introducing the C++11 atomics into CUDA, they had Alloy to help them a lot with proving the behavior of the memory model, whether they actually modeled C++11 memory model.
it's very useful when you have to let the model generate for you the automated reasoning, because sometimes it introduces scenarios you haven't thought about.
Yes.
And actually develop. So not always to run the whole thing, but actually learn from it how you review it.
Yes.
Okay.
I'm going to quickly see if there is some here. No. Okay, any more questions? Yes.
This is Peter. Return to the snippet which you demonstrated or compile formats. Use the language mechanic.
Give me a moment. Dynamic to like no, that's too much. Blank compiler warnings. This one.
Yes, I would like to ask.
What the bug?
For me is like the pretty simple here, like but the real problem is very different because you don't want to make unique with a single char. You want to make unique with char array, right?
What is it?
What to the
no.
intent of the code, but this well
So the main
primitive varied code and syntactical. Just I'm wondering if code analysis finds this. So yeah. Maybe an
if you mean that it doesn't use the char array, then the answer is I don't remember. I would have to check.
I'm pretty sure you can make it.
If you can make a unique for the char array, if you do the array allocator, give you an create an array that like has no boundary checking, no exertion, no methods other than a C array, except that is automatically destroyed.
It's actually useful if you need to do some low-level stuff.
I don't think the question is if you can do char array, which you can do, obviously. The problem is that this should give you an array, but its size. And
That was not.
I don't think from static analysis.
Yeah, that's the truth. It doesn't do a char array. It just creates in dynamic
Char,
allocates 1 byte.
valued to this.
And that's the value that validator gets.
Yes, but the question is, can your tool tell you this? And I would expect that the LLM will complain about this.
Well, yes, but the others would not complain about this.
But I said probably not.
Well, I guess your compiler would start complaining when you try to get the substrate, the indexing operator there,
Yes,
because it becomes impossible to compile. So that would be correctly path if there was a more realistic scenario.
yes, but it's actually a very good catch.
Another
Yes.
you note about dynamic analysis tools that they have very low false positives. That it depends on the quality of the tool. Because
So yes,
I try to use the synthesizer implemented in Microsoft Visual C++ compiler, and it was absolutely chaos. That was a found like next let's say invalid addressing when you just try to read static read literal, because it was like 16 bytes from another strict literal.
uh, so if you mean like it found issues when you accessed like some globals, then that's a compiler of issue. Because so the other sanitizer needs the compiler to do the right thing, which means properly instrument all this stuff. What is actually like massive pain is the memory sanitizer. Have you tried it? Memory sanitizer. No?
Is that different colors?
Yes, you have address, memory, thread, undefined behavior sanitizer, and then bunch of others because they are multiplying. And the memory sanitizer requires your std-lib implementation to be compiled with memory sanitizer to work, which very few people actually do. So, about once a year, I get someone complaining on the Catch2 issue tracker that they tried memory sanitizer and it found lots of like bugs from startup of Catch. My question is always, memory sanitizer, okay, have you instrumented your std-lib? I have to do that. Yes.
Actually, what I did, I just read the documentation for address sanitizer in Microsoft Visual C++, and I did everything to. I didn't like improvise, so just did everything as they requested, and it started to find.
It's possible.
Processes and
Like okay, so I have never had this issue with client-based ASAN, but I know that when then the MSVC ASAN first came out, I tried it once and didn't even compile, and I just went nope. Sorry.
So I have experiences tools and the
Oh, definitely. Like I have lots of bugs reported against Clank ID, Clank, GCC, MSVC, and so on. Tools are written by people as well.
I have one suggestion for improvement, and this will maybe help you with LLMs. You need to rename your function from better C to perfect C.
Yes, that's a great one. But that was actually a thing I tried.
As was actually on their religious drone because singing.
It was actually one of the many tabs I tried. Like what if I change the names of the function? It started complaining about the names being stupid, which is true. But they didn't complain about the implementation bug. So
Always argue that the bad code is not.
yes.
I was actually, there is a joke that any code can be shortened by one instruction, and every code has a bug in it, which will lead you to code this one instruction with this buggy or fix something like that. I was kind of expecting it will go down that way eventually, but no, it hasn't.
Okay. Any more questions? No, then thank you for listening. Yes.
I used to be like some kind of framework for us called Verus, and in the whoever, right? So if I
Verus. I don't remember hearing about it. So what does it do?
lexical mechanism to introduce raw verification that into like the s.r.o, and it should somehow be able to formal verify like certain functions or something like algorithms. I was wondering whether there is something similar also to C++. Have you heard about something similar?
No. And you said Verus? I'm going to make a note.
I see. Is it something you can also work under the symbols? Oh, I know that.
Well, really, you like bright from outside, so knowledge so. But well, to be honest, like there might be other tools, right?
Yeah.
I'm not familiar with the C++ version, so
Okay, yeah. It says here that it supports some subset of Rust. I would have to check like what subset. This is generally the issue with formally verifying the code. Like the full C and C++ language are terrible to reason about. And Rust has a lot fewer of these issues, but it has some of them still. So yeah. Yeah, the big issue in C++ is just, okay, this is a pointer. Now it points somewhere. I changed it. What has happened now?
The best part is the unity intentionally so that people as well on house and as activities. There is like a ebook, the cultural commentary, and kind of describe the evolution of the language and all the different things that they did to the language just so that people learn on silly hardware.
Well, thankfully, at least some of the silliness is being slowly standardized away. Like we can finally say that integers are two complement. We can't tell you what happens when it overflows, but we can tell it's two complement. It's not some special representation of whatever. So some of it is slowly going away. Some of it has actually gotten worse because the memory model in C++ is great and also definitely wrong in some places. So it has been, I think we have been, well, not me, but the committee has been trying to standardize away. It's really hard.
Because
Optimizations, but also some like you want. Yes, and basically,
in Linux, like memory barriers don't text.
yeah, basically the issue kind of is that we want to have this like memory model with different atomic levels, sequential consistency, which you shouldn't use, equa release, which you should use, relaxed, which you should use if you know what you are doing, and all this stuff. And then we found out that actually, after all this, then we can't quite forbid some behavior. That would be obviously wrong. No hardware does it, probably. But we don't know how to specify that it's wrong. It doesn't also destroy other desirable properties of the memory model. If you have ever heard out of thin air values or execution or similar stuff, that's one of the big issues. Okay, anything else?
Can you talk from Zoom online?
There is some message on Zoom, but I can't read it. So if nobody here has a question, then we are done. It's time to go